Any scientists know that it may happen that a big one is arriving. Of course, they were not sure that it was a safe situation, but they said that it was because they wanted to avoid the reaction. So, I mean, the intention was good, no doubt on that, but it was a mistake. And this is an example of a mistake. Of course, I could say several, I could probably enumerate several other cases in which neglecting uncertainty had a positive effect. But one thing is an emergency situation, another thing is a design. So you have to evaluate. I'm not saying that you as an engineer, as a scientist, need to be, I mean, always admitting your uncertainty. If it is an emergency situation, you have to evaluate case by case. But when you are designing, I mean, I don't see any real problem. But
can you explain again what do you mean with robust method?
Robust?
What do you mean with the robust method for assessing the health?
Yeah. Okay. Robustness is defined in science. Okay, there is a definition of robustness. Let's look on Wikipedia the definition, and then I explain it to you in technical terms what means robustness. Basically, first the technical explanation. A robust approach is an approach that may be not very precise, but not very wrong. So robust means that you take the safest way to get to target. And let me provide you with an example. If you decide to select a very complicated model to provide the required answer, which means a lot of parameters, the model is more refined, so in ideal condition works better, but it's also subjected to high uncertainty. In not ideal condition may be completely wrong. And let's compare iMod and the linear reservoir. The linear reservoir is more robust than iMod. Because, okay, it's not very detailed, so it doesn't work well, but it's not, it's safer. Let's look on Wikipedia now. Okay, you can read here. Robustness is the property of being strong and earthy in constitution. When it is transported into a system, it refers to the ability of tolerating perturbations that might affect the system functional body. In a non-ideal situation, the model can tolerate it. Okay? And objective, I think I don't need to explain what I mean. And you know, I say objective, I insist on objectivity because when we talk about human impact, it's always controversial, always. And on water resources, I'm saying. In general, I would say it is controversial, but on water resources, it is extremely controversial. So you need to be very objective and robust because, you know, it's, think about, let me give another time the example of climate change. In climate change, basically, the assessment of the driver and their priority is done through climate models. Climate models are models that try to reproduce the circulation of the atmosphere, the circulation processes in the atmosphere by taking into account ocean circulation, by taking into account the hydrological events, everything, and they try to reproduce the climate system, the behavior of the climate system through a numerical model. There is a lot of uncertainty, and there is a lot of uncertainty because, you know, it's already difficult to describe the hydrology of a catchment. If you think about the climate system, there is a lot of uncertainty. Keep into account that the climate system, we don't know it in detail. And they run this model to make predictions for the future. The models are highly uncertain, but uncertainty is often neglected. I don't think they are robust because they work with this very relevant uncertainty that makes the model not robust, and usually uncertainty is neglected. Not always. There are some climate modelers who admit that. And But there is the general tendency in the climate science to minimize the effect of uncertainty because it undermines the credibility. And I mean, it's reasonable. Climate scientists believe that the climate is a real problem. Climate change is a real problem. And if you speak with them, it's amazing because, I mean, they are very convinced. And I spoke with a climate scientist recently, and he told me it's the main risk for humanity in the next 50 years. Above terrorism, above what else? Above water shortage, climate change is the main risk. So they are very convinced of that. So if they are very convinced, of course they say, and they admit it, if we don't claim that we are sure, we are not believed. So we have to claim that we are sure of our opinion. Okay, that's fine, but you are an engineer, and what is the problem? The problem is that if you take for sure, for granted this prediction of these models, these are very bad predictions, and if you take into account that, your project increases in cost a lot, and often it's not doable. This is an experience that I had several times. You plan a water resource system, you are required to take climate change into account, you get model projection, the cost of the infrastructure goes up, because if it's a dam, you have to double the size. It becomes impossible to realize, and nothing is done. So this is, I hope, clarifies the example. So when you get to this step, it's extremely important. So how can I quantify it? This is relatively easy. Once that you have a model, you develop the future scenarios. And the model may be a probability distribution. It may be an IMOD model. I mean. And then uncertainty assessment is another tricky point. Okay, so perceptual assessment. We already said that the debate is quite interesting, and the result is that it's not very clear what are the most important impacts, and therefore here you are required to give your contribution in the discussion. And it may be easy, I already said that, it may be easy if it's a water withdrawal, if it's something that is very clear, or it's also easy urbanization. If you urbanize a catchment and you know the area that is paved, it's easy to identify the human impact. We are used to do that. Think about a sewer system. A sewer system, it's a system that is designed in order to remedy to the human impact. The human impact is urbanization, which implies that water doesn't infiltrate anymore, and therefore we need a sewer system. How do we design the sewer system? By taking the area that is urbanized, multiplying rainfall for that area. This is very simple. This is something that we are used to do, and we started to do 100 years ago or more. Fine. But in other cases, it's more difficult. Okay. It's more challenging. Okay, and we need to be aware of the most frequent and important drivers. You have a question?
Yes, I'm not getting what you mean with drivers.
Oh yeah, forcings.
Or
no, yeah, this is a good question. Okay, no, the human impact basically has an effect on water resources, and understanding how this takes place, this is what I mean with drivers. So if the human impact is a water withdrawal, the withdrawal is the driver. And yeah, but here I speak about drivers of human impact. Yeah, because we are talking about an effect of human on something, water resources, and with drivers, I mean how it happens. Okay, this is what I wanted to say. So, quantify what is the process which makes the human impact happening. This is the driver. So, a water withdrawal is a driver. A climate change is a driver, because it's an effect of human impact. We believe it's an effect of human impact. Actually, climate change may be also natural, but let's say it's an effect of human impact. And the process with which the human impact affects water resources is climate change. This is what I mean. So you have to identify if you have withdrawals, if you have climate change, if you have increased evaporation. These are the drivers. Okay. And okay, these are some examples. So we already spoke about it, but let's discuss them. So climate change may be also local. Don't forget that. We are used to hear about climate change, to listen to people discussing about global climate change. It may be local climate change. Local climate change can be, I think we already discussed that, can be very relevant. And the most relevant example is the heat island effect. We urbanize and the temperature in the cities increase about 2 degrees. And this is a significant increase. When we talk about global warming, we talk about 1 degree, depending on the location, in the last 150 years. When we talk about the heat island effect, we may speak about 2 degrees in the last 20 years. Because today also with the diffusion of air conditioning, indeed the heat island effect was exacerbated a lot, increased. And so don't forget about it. And also your colleague made the example of the Urmia Lake the other day. It decreased evaporation. If you reduce the extension of a lake, you decrease evaporation. This causes indeed a local climate change that may be very relevant and imply a decrease in water resources because there is a decrease in evaporation. Water evaporates somewhere else, but not there. And therefore the local climate is influenced. So if they took the water from the lake for bringing it somewhere else, it evaporates somewhere else. I don't remember what, yeah, because they dammed the rivers. So basically water evaporates upstream and there is a local climate change. What I suggest, let me see if, yeah, this is the last thing that I forgot to discuss. Other impacts, river training. River training, it is important, and not only diversion, but also river tunneling. It's maybe a relevant impact. And also when you build levees, when you take into account that you are changing the regime of the river, and therefore this can be indeed very relevant. So for instance, on the risk of flooding, river training is an extremely important driver. If you see that river training took place, or extensive river training, or is planned on the risk of flood, this is extremely important to consider. And this is something that we forget often in Italy. Many of the tragedies that happen in Italy today, they are attributed to climate change, but they are not indeed, because if you go there and you study the situation, you see that the reasons are other reasons. And this is extremely important, because if we want to mitigate the risk, we have to recognize the drivers. Okay, and land use change, okay, I already spoke about it. But how can we identify these impacts? My suggestion is, these drivers, how can we give a priority? And especially because we have to convince people and we have to provide the right information to people in order to elaborate their decision. So how can we do that? My suggestion is to go to subdivide the complicated decision, like 15 possible drivers. My suggestion, which is also, it's not mine, it's not my idea, it's a common procedure in decision making. What is suggested when you have a very complicated decision is to split the complicated decision in simple decisions. So if you have to classify 15 drivers, let's first of all divide them into groups. The most important and the less important. And this is why I suggest here to first classify hard and soft facts, hard and soft drivers. So let's divide them into groups, and this is the proposal that you can make to your audience. Okay, the decision is very complicated. Let's try to agree at least on what are the most important and what are the others. The others are not forgotten, are not neglected. Just let's identify a priority and let's split them into groups. Hard and soft facts. A water diversion is hard because it's something that it's planned, I have the project, or something that already happened. It's hard. Climate change may be hard. If you have data showing that it's hard, it's hard. Instead, if we don't have any clue of how climate change may happen, okay, let's try to see if we can put it in a second priority. So this is my suggestion. Let's try to divide between hard and soft facts. It's not easy, but of course this is something that you can mediate. So one may say like 15 drivers, let's identify the 5 most important, and then for reaching an agreement you can enlarge the group. You may say let's identify the 3 more important, and then people don't agree because 3 is too less. And then you can mediate it by saying, okay, let's extend to 5, let's extend to 6. It becomes a matter of finding the optimal solution depending on your audience. This is something that it's not our subject. Decision theory is not our subject. There are, university courses dedicated to it. But I have the feeling that at the end of the story, in most of the cases, you need a personal interpretation, which of course is supported by your experience, by your studies, but at the end of the story you have to really elaborate a personal contribution. And therefore, it's really, the theory does not suffice. The theory is necessary but not sufficient. Okay, but the proposal is, okay, let's split into groups. And then this is an example of hard facts. Demographic expansion. This is a driver of change, of human impact, which is something that we cannot neglect. So if we are planning a water resource system to serve a city with 100,000 inhabitants, and there is a plan that demographic expansion is continuing, this is art. River diversion is art. River damming. You plan to build a dam, this is an art fact. And for sure the availability of water resources is changing after that. River training. Groundwater withdrawal is like river damming. If you see that people are taking water from wells, very often we don't know how much water they are taking, but we know that there are wells. This is an art fact of human impact. No doubt on that. Extended and substantial land use change, including urbanization and deforestation or reforestation. This is an art fact. Local climate change in climate-sensitive areas. This is an art fact. For instance, in the Alps, we don't know why, but global warming, the warming in the last 100 years has been higher than the average at the global level. At the global level, we talk about 1 degree in the last 150 years. In the Alps, we talk about 2 degrees. In the Alps, we don't have a situation where water supply depends only on snowmelt. In other situations, like in the Andes, indeed we have cities that rely on snowmelt for water supply. And global warming, for them, it's a problem. It's an hard fact. Because during the summer, for reducing the area, the area covered by snow, is reduced in the last 30 years, and during summer they suffer from lack of water. Soft fact, just an example, and you can add your soft facts. Global and local climate change may be soft because at the end of the story, this is what we see. I mean, at the end of the story, we see that climate change may be very concerning, but unless something very sudden happens, it's not yet a soft, an hard fact. Sea level rise, it's not an hard fact. We are talking about millimeters, fraction of millimeters per year. Unless something really sudden happens, because there are theories that predict that after a certain threshold of warming, the ice cap may disappear in a few years. So unless something really concerning happens, sea level rise, it's not an hard fact. Local land use change will reduce the impact on freshwater resources. Maybe urbanization, maybe that it doesn't affect your water resources if water resources come from a different place. Changes of social and environmental condition may be also not so relevant if they are proved, if depending on the project you are dealing with. And the status of water distribution system may be not so concerning. And because, you know, today there is a renewed interest on these water resources systems that are getting aged, and therefore people say, what should we do? And in most of the cases, I realize that these concerns are not so relevant, because it depends. I mean, if it's a dam, and there are indeed signs that the dam is getting in a critical situation, it's relevant. If it's just a matter of something, distribution systems, maybe not so relevant. It depends, of course. And then a second step. Okay, we divide between the more important and the less important, but still at the end of the story, we have to this hard fact give a priority. And how to give priorities? Again, I'm talking in general, but there are specific situations where it's easy. There are other situations where it's not easy, and even if you have to give priority to 4 or 5 objects, it's not easy. So for what reason we need to give priorities? And I want to give you an example. But the reason is that if we want to mitigate the impact, if we want to take it into account, we absolutely need to give priorities. Because given that there is uncertainty in our design, and given that these impacts may lead to situations where finding a solution is difficult, at the end of the story, if we need to identify a solution, we have to give priorities. If we decide that object I is high priority, we select the solution that resolves the problems of object A. And object B, we may say, okay, it's lower priority. So I may find another way to solve the problem of object B. Let me give to you a more specific example. Let's suppose that you have to get water from a river for feeding an hydropower plant or agriculture. Hydropower plant or agriculture. Okay. Then you have an impact caused by this intervention, which is the benefit that you get for in terms of hydropower value. And this is one thing. And then you have a problem because the plant is noisy, and therefore you have a negative impact on the local population because of the noise. Okay, then at the end of the story, what you are required is to identify the design flow for this plant. If you increase the design flow, you increase the benefit in terms of idle power, but also you increase the noise. It is extremely important to give a priority. The prioritary need is to eliminate the noise, or the prioritary need is to produce electricity. And giving a priority means, in this case, to find an economic value. So I find an economic value of the benefit from electricity, and I find an economic value for the disturbance given by the noise, which means I go to the person and I ask, for instance, how much money do you want in order to be able to tolerate this noise? And then I may reach a compromise by giving priorities in terms of economic value. If I see that the economic value of electricity is very large, of course I can afford the expense of giving some money to the stakeholders that are concerned by the noise. If I see that the economic value of the electricity is much lower of the economic value of the disturbance, then I may decide not to make anything. And what I am needed to do is to find the design flow which is the best compromise, and the best compromise requires assigning a priority, in this case an economic value. In other cases, the economic value may not be a good quantifier of priorities. It depends on your case. Now, how to move forward? There is, in the literature, in the decision theory literature, there is an extensive information on how to decide between competitive needs and therefore how to assign priorities. This extensive literature recognizes that assigning priorities is extremely important and proposes some objective methods. This is not our purpose. We don't want to investigate this process of decision making, and it is typically dealt with in the courses focusing on water resources management. I don't think it is our task to go into the details. I just want to mention, and it's mentioned here, that one of the possible methods to assign these priorities is pairwise comparison. What is pairwise comparison? In poor words, let's suppose that you identified 3 drivers of human impact, 3 kinds of human impact. I always specify what I mean for driver. Okay, we cannot give a priority. We cannot say the 1 is more important, 2 is more important, 3 is more important. The idea is, let's compare them 2 by 2. So let's compare one driver 1 with driver 2. What is the more important? And you ask your stakeholders just to say what is the more important, not to assign a value. Just to say, tell me what is the more important. Okay, more important is 2. Perfect. Now let's go 1 and 3. What is the more important? The most important. And they say, the most important is 1. Perfect. Now 2 and 3. What is the most important? The most important is 3. And then there is an analytical construct that gives to you the priorities in terms of weight. Weight summing up to 1. And you have also a mean to check the consistency of your replies. Like in the examples that I made, I was not consistent because I said that 2 is more important than 1. 1 is more important than 3. 3 is more important than 2. It's not consistent. I explain better. 1 is greater than, no, I said 2 is greater than 1. I said 1 and 2, yeah. 2 greater than 1. And then I said, let's focus on 1 and 3. And I said 3 is, let's see if I am consistent. 3 greater than 1. Don't look at the number, I mean, because just look at, let me do like this. where the major and the minor means more important. And then okay, so if 2 is more important than 1, then if 3 is more important than 1, we are still consistent here. So let me make this. 1 is more important than 3. And then I say, so if 1 is more important, 2 is more important than 1, okay, 1 is more important than 3. And then if I say that 3 is more important than 2, in my opinion, I'm not consistent, yes. In this case, I'm not consistent. Yeah. Let me see, because 2 is more important than 1, 1 is more important than 3, and then if I say 3 is more important than 2, I'm not consistent. And there is, anyway, an analytical framework that tells you at the end you are not consistent. And the answer is not yes and no, it's an index of consistency. So basically, when you make this pool in your audience, you ask a stakeholder, you may ask, for instance, each stakeholder to give its own reply. You have an analytical means at the end to tell your respondent, look, your response is not consistent. Think about it again, because this is not consistent. And this is quite objective. And usually people in this way get more convinced, because it's easier for them to understand what's going on, because they compare things 1 by 1, 2 by 2. And then at the end of the story, you may say, okay, this stakeholder was consistent and ended up with weights, so W1, W2, W3, which you can compute analytically. There is an analytical framework for it. This is a possible way. Of course, in this case, with three objects, it's easy, but think about 15 objects. It's much easier to try to reduce this 15 to a subset of hard facts, if it's possible. And then when you get to 5, 6, you compare them 2 by 2, and then at the end of the story, you decide what is more important. And if you want to get more on the web page, more information, on the web page there is a link for it, but it's very easy. You make on Wikipedia here, Pairwise Comparison. And here you have the description. Is any process of comparing entities in pairs to judge which of each entity is preferred. And here there is a very nice example, if you want, but it's not here, let me see. Okay, one kind of pairwise comparison is the analytical hierarchy process. And there is here an example which is very nice, and if you're interested, the example of choosing a leader, this is on Wikipedia, it's very clear. I mean, it's very easy to understand. And this is the example, of course, of a personal selection process, but can be applied also to, at the end of the story, it assigns a weight to the person. And it's not useful, this example, for going through an interview. So, but it's a useful example for clarifying what is pairwise comparison. I'm not interested in this, meaning that at the exam I'm not asking this. The only thing that I may ask you at the exam is how can we assign priorities? And if you say through pairwise comparison, it's fine to me. And I'm providing this information because if you want to expand, I think this is an interesting thing that you may look at. And actually, this analytical hierarchy process, I think there is also a link to one of my papers in my web page. This it's frequently used in water resources design. Okay, let's go back to our presentation. Now, when we talk about methods, now we move forward to the next step, method identification. And I talked about a robust method, and I talked about robust and I said objective method. And I made the example of climate models. I want to give more details, so I moved one step forward, methods. For once that we have identified the priority drivers, I identified climate change as the priority driver. Okay, now my problem becomes how to quantify it. And I need to quantify it because I need to take into account the driver into my design. Okay, so one possibility, we already discussed it, is models, but we will discuss models later. There is another possibility, so let's split the methods in two categories. One category is data analysis, and the other category is modeling, like we did for water resources assessment. We talked about direct method and indirect methods. Let's make a similar classification here. So, again, what is our problem? We have to quantify a driver, to assess it, to assess a kind of human impact. Let's suppose that it's not trivial. If it is a water diversion, it's trivial. We don't discuss it. In general, we can say that you can move forward by using information, data typically, historical data analysis. Let's move in a more general framework, data analysis, because historical means that they are old data and implies. Let's suppose that they are data. And then another category is models. Okay, let's focus on data. Usually, when we talk about human impact on water resources, we refer to historical data analysis, and then we come to this slide.